I want to talk about, so last time we finished talking about L'Hôpital's rule. That will be on the quiz next time around. I am ready to move on to the next bit, and the next sort of section is, we've been in chapter 6 in the book for a while, which was generally about inverse functions, which included the inverse trig functions, but also the logs and exponentials, which are inverses of one another. And then for some reason, the L'Hôpital's rule, which to me doesn't really fit into that chapter, but they got to put it somewhere, I guess. The next chapter is chapter 7, and it's all about integral tricks. So basically the only sophisticated integral trick that we have so far is the U substitution, which we are going to continue to use fairly often. But today I want to get to the first, and this is a fairly straightforward integral trick, which is sometimes necessary when the U substitution doesn't work. And this is called integration by parts. So it is similar in spirit to the U substitution in that it involves looking at an integral and sort of picking out, I want to call this part, we still use U's when we do integration by parts. You look at the integral and say, I'm gonna call this part U, and then you do some other stuff, although it's different from the substitution, the stuff that you do. The substitution, the U substitution, is based on the chain rule, and it's basically an antiderivative version of the chain rule. The integration by parts is based on the product rule. So this is an integral trick which comes from the product rule. There is no real product rule for the integral, but the closest thing there is to that, I suppose, would be the integration by parts. So this is an integral trick based on the product rule. And I will just refresh our memories about the product rule. I'm going to write the product rule in a somewhat weird way. Rather than derivative, I'm just going to write D. D means derivative, right? The product rule says D of a product, U times V, and everybody knows the product rule. It is the first thing times the derivative of the second thing. That would be U dV, writing it this way, and then plus the second thing times the derivative of the first thing. That would be V du, all right? This is a product rule written in a strange way using a D rather than a, usually I would write D over dx or something, but whatever. All right, and this, the reason I wrote it with D's like this is we can do the integral on both sides. On the left, we get integral of d uv, and on the right, we get integral u dv plus integral v du. Unfortunately, I hope your handwriting makes it obvious the difference between a u and a v. You must be able to tell them apart, or else you'll get very confused when you're trying to do this. I write my u's with a little tail on them for this precise reason. All right? And then just to sort of simplify very vaguely, on the left side we have antiderivative of derivative of u and v. This ends up being just u times v, right? Because the integral and the derivative cancel out. So this says uv equals integral u dv plus integral v du. And one last thing is I'm going to just subtract stuff around. I'm going to rearrange, put u dv on one side by itself. It'll say, sorry, I meant integral u dv, and then if to isolate that, I would subtract integral v du in the thing above there. It says this, uv minus integral v du. And this, my friends, is the integration by parts formula. It comes from doing the product rule and then just kind of rearranging stuff, writing it using integrals instead of derivatives. But this is called the integration by parts formula, and you need to memorize this, although we're going to use it often enough that I think you will just naturally remember it. But one thing that's nice about the integration by parts is there's like a specific formula for it. So unlike, say, the U substitution is a lot more wishy-washy. The U substitution is like a procedure. You have to remember how to do it. The integration by parts formula, at least, is just a formula that you plug stuff into. Although it's still up to you to decide how to choose the u. But this is the integration by parts formula. Integral u dv is uv minus integral v du. So the idea here is you look at your integral, and just like in the u substitution, you must choose for yourself which part. So you start with the left side, and it has a u part and a dv part. And you have to decide which part I'm going to make the u and which part I'm going to make the v. So you look at your integral and choose which part is the u and which part is the dv. And just like the u substitution, there are no real rules for this. There are sort of a bunch of general guidelines, and when you do more and more examples, you'll begin to get a feel for what are the kinds of things that you generally want to choose to be the u and what are the kinds of things that you want to choose to be the dv. All right, but that comes with just practicing a bunch of examples. This is the basic idea. Let's just try everybody's favorite first example of integration by parts is this, x times e to the x. This is a classic integration by parts integral. X times e to the x. When you see that multiplication in there, x times e to the x, the fact that there is a multiplication right here means you're going to have to do something sophisticated. Unfortunately, in this case, u substitution just doesn't work. If I were trying to do the u substitution, I might choose u to be the inside of this, which would be just x, but that's not going to give me anything to handle this x on the outside. And in fact, there is no way to make this work using the u substitution. Instead, we're going to do parts, and just because I know how these things generally go, I will say these are my two parts. That's going to be the u, that's going to be the dv. Now we'll talk in a few minutes about how do you decide which is which, but for now let's just see how the thing actually works out if I give you the choice. All right, so over on the side, just like when I'm doing u substitution, I'm going to write, okay, u is x, and then dv is e to the x dx. So one little bit of commentary here is that dv always includes the dx part. Right? Your integral that you start with always has a dx in it, and that always you need to make part of the dv part. All right, but usually the dv part has some other stuff in there too. In this case, I chose e to the x and dx to be the dv. Okay, those we choose from the integral, and then it's up to us to figure out. Now we intend to use the integration by parts formula, which is up there, but you'll notice the integration by parts formula involves du over here, and it also involves v, and we don't have those. So we choose u and dv, and then we calculate ourselves, we figure out on our own what is du and what is v. And these you do by taking derivatives, just like in the u substitution. If u is x, then du would just be 1 dx, right? Du is always the derivative of u. So this is 1 times dx. And the v is the integral, the antiderivative of dv. So if you have u, to get du, take the derivative. If you have dv, to get v, you take the antiderivative. And anybody can tell me what's the antiderivative of e to the x? I know you love it. It is e to the x. Yeah, e to the x, the derivative and the antiderivative are always e to the x. So here, v is just going to be e to the x. All right, and you'll notice after we do this part, the du now has the dx in it, and the v doesn't anymore. That's because the v is the result of doing the integral of this. And the dx will go away. Yeah?
Do you have to do a plus c when you take the integral of dv?
No. This is a good question. The plus c is handled sort of later on.
Okay.
You'll see where it goes. It's not wrong to put it here, but it's easier to just add. You do basically just tack it on at the very end. Although you could insert it here, it makes things look a little more complicated. All right. So maybe I'll just make my sort of commentary over here. The dv always includes dx. For this step here, you find du by the derivative of u, and v is the integral or the antiderivative of dv, all right? So it's similar to the u substitution. You choose u and then you take its derivative to get the du. You also choose dv and you take its antiderivative to get the v. All right. But anyway, once you figure all of that out, we can plug into the integration by parts formula. So now we plug in, and it says integral of u dv, that's what we started with, is, I'll just write the formula, uv minus integral v du, right? And so what we get in this case is u is x, v is e to the x. I'm just plugging stuff in directly. Those guys are not inside of an integral anymore. They're just hanging out there. And then minus integral v is e to the x, du is dx, right? 1 times dx. So we just plugged everything in. Now, we're not done with this whole problem at this point because there's still an integral here, but hopefully this integral is now easier than what we started. And this is similar to the u substitution. You know, after you do the substitution, you still have to do the integral of something, but the whole point of the substitution is that you started with the hard integral and you turn it into an integral which is easier. And that's the idea here also. We started with the hard integral. Now we result in this thing which we still have to do this integral, but this is an easy integral now. This is just e to the x, and the integral of that is e to the x. So we're not done because we still have an integral to do, but that stuff stays like it is, and this just becomes e to the x. And then, finally, we just put the plus c at the end. All right. The fact is, you end up doing another integral here, so you might as well just put the plus c here, although if you want to be cute about it, you could insert the plus c earlier. It has the same effect though, so we just put it at the end. Don't forget the plus c. Don't forget the cupcake, as they say in my kids' high school class. I don't think anybody else ever says that. This is the answer though. All right. Any questions about that? As always, we can check our answer if we got a few minutes extra on the test. How would I check this? I would take the derivative of that. So here's a little check the answer. The derivative of that. What I see first is x e to the x. We have to use the product rule for that. It would be the first thing, which is x, times the derivative of the second thing, that's e to the x, plus the second thing, e to the x, times the derivative of x, which is 1. That was just from this guy. And then I go minus derivative of e to the x is e to the x. And the c, of course, goes away because it's a constant. And here you can see these guys will cancel, and the answer is just x e to the x, which is indeed what we started with inside the integral sign. So I feel good about that. It really worked. All right. This is what I would say is like the basic integration by parts example. This is an easy one. All right. It relies on you knowing how generally to choose the u and the dv. So I'm going to tell you some basic principles here. In the u substitution, I would say generally you choose the u to be the inside of something. That's not really the case here. So you have to sort of do a bunch of examples to get a feel for this, but choosing the u and the dv, all right? First of all, the parts formula only works for multiplication, right? If you look at the integration by parts formula, it's all about integral of u times dv. If you see fractions or other stuff in here, you're going to have to rewrite it in terms of multiplication to begin with, because the integration by parts formula is only about multiplication. But anyway, choosing u and dv. So I will just say as like a preliminary thing, each must be a factor multiplied together, right? If there's like stuff being added together, you don't want to use integration by parts on that. Parts is only meant for things that are being multiplied together. All right. Anyway, what about the decision? So as far as choosing the u and the dv, if we look at the example that we just did, I would say, why did this work? Why it worked is because we started with x and e to the x, but after we did this, we had 1 and e to the x, and it got simpler, all right? The idea is you want to choose things that get simpler when you do this to them. And specifically what that means is you want to choose the u to get simpler when you take its derivative. and you want to choose the dv to get simpler or maybe just stay the same when you take its antiderivative. This is the basic idea. So I would say this is not a hard and fast rule, and sometimes you have to violate this general principle, but in general, I would like to choose u to be a part which simplifies or maybe stays the same when we take the derivative. So in that example we just did, I chose u equals x, and that's because the derivative of x is 1, which is simpler. All right. So we choose u to be a part which simplifies or maybe stays the same when we take a derivative. So specific, examples of that could be like polynomial. If you see like x squared, when you take its derivative, it turns into 2x, which is easier to deal with. So a polynomial type thing always gets simpler when you take the derivative. A natural log of x also gets simpler. ln of x will turn into 1 over x, which is usually easier to deal with than a natural log. So that's another good choice to choose as the u. Something like, I would say sine or cosine. They don't get simpler, but at least they sort of, they don't exactly stay the same, but a sine will turn into a cosine, or a cosine will turn into a sine, which is not getting any more complicated, at least. Or sometimes e to the x. And again, e to the x doesn't get simpler when you take its derivative, but at least it doesn't get more complicated. So sometimes e to the x is a good choice for the u, all right? So this is like, these are good choices for the u. U be like polynomials, ln, sine, cosine, e to the x, that kind of thing. And what about the dv? It's the other way around. So a dv should be something which gets simpler or doesn't, or stays the same maybe when you take the antiderivative. So usually a polynomial is a bad choice for the dv. Anyway, dv should be a part which gets simpler, although in practice that usually doesn't happen. There aren't a lot of functions which get simpler when you take the antiderivative. But anyway, should be a part which gets simpler or the same when we take the antiderivative. And dv be like, e to the x, sine, cosine. Those are typical things that you choose to be the dv, all right? You should not choose ln of x to be the dv, because the integral of ln, actually we've never even talked about. Taking the antiderivative of ln x doesn't get easier. And generally, polynomials are a bad choice for the dv because a polynomial like x squared will turn into 1/3 x cubed, which is even a higher degree polynomial. All right, these are general principles. Like I said, sometimes you need to break these rules. There are some examples where you actually do want to choose a polynomial for the dv, but these are the general idea. All right, I got a few more examples of these, and then I have some for you all if we have time. I think we'll probably have time. All right, how about this one is a little more complicated looking. E to the x times 3x minus 2 dx. All right. So I do see multiplication on the inside, which means I am thinking about doing integration by parts here. And the two parts apparently are e to the x and 3x minus 2. Those are my two things which are being multiplied, and we have to decide which one to make the u, which one to make the dv. Anybody want to say, in the spirit of my recommended choices up there, what do you think for the u?
3x minus 2.
Yeah, let's take 3x minus 2 for the u part. That means the dv has to be e to the x, and like I said before, the dv part always includes the dx. That's because the dv is something that you're going to take the antiderivative of, so you want the dx to be in there rather than in the u. All right, those are my choices. I like these choices. Now we figure out on our own what is the derivative of u. That's the du. Somebody want to say? Shout it out. Yeah. 3. 3 dx. I heard her say in her heart, the dx part. Yeah, the dx should be included in there. And then the v. V is the integral of dv. This will be, if you want to write it out, it's the integral e to the x dx, but that's just e to the x, right? Excellent. So I think we're ready to plug everything into the integration by parts formula. Remember, the formula is uv minus integral v du. If I say it enough times, maybe we will all just naturally remember it. uv minus integral v du. What is it? What is it? I just plug everything in. So u first, 3x minus 2 times v is e to the x, right? Make sure you put those parentheses in there. They matter. And then minus, that was the uv, minus integral v, that's e to the x, du is 3 dx. Right? And now we just have to do that integral there. Sometimes it's helpful to try to simplify that integral before doing it. Anybody, is there anything we can do here to simplify it all? I'm concerned about how do you handle this multiplying by 3 on the inside? Yeah? Yeah, just factor the 3 out. Remember, a constant multiple inside of an integral can always be just moved all the way out to the front outside the integral sign. So this is not doing anything here. Minus 3 integral e to the x dx. And then we can do the integral e to the x is e to the x. So my final answer is going to be this guy, and then minus 3 e to the x. Let's see, like that. This is how we do it, integration by parts. It's not so complicated, in my opinion. I think actually, to me, this is maybe a little easier than the u substitution part, just because the process of plugging into the formula is fairly straightforward, whereas the process of making the u substitution fit is sometimes a little tricky. All right, let's try. I have 2 more, and then I have some for you all to try. Okay, how about 3x cosine x dx? Integral 3x cosine x. All right. Again, parts comes to mind just because I see multiplication in there. 3x is one part and cosine x is the other part. Although you could put the 3, I suppose, together with either of them. Anybody got a feeling about this? What should I pick for the u? Yeah. How about 3x? Yeah, I like that. Generally, if you see part of it is a polynomial or just like a power of x, that's usually what you want to choose for the u. So I'm going to pick 3x as the u. That means the dv has to be the rest of it, cosine x dx, right? Now, actually, if you like, you could have just taken the 3 out of the integral at the very beginning and ignore the 3 for the rest of the whole thing, but you can include the 3 as part of the u also. Okay. Take the derivative to get du. That means du shall be 3 dx. And then v is the integral cosine of x, which is sine of x. The antiderivative of cosine is sine of x. Right? And now we do the integration by parts formula. So it is uv minus integral v du. We get 3x, that's the u. V is sine x minus integral sine x times du, which is 3 dx. Anybody got a suggestion? What should we do next? We have to finish by doing that integral somehow. Yeah? Pull the 3 out. Great. Yeah, factor the 3 out of that integral. And then do it. 3 integral sine x dx. And then integral of sine x is negative cosine x. So this is 3x sine x minus 3 times negative cosine x. That's that. You could write that as plus 3 cosine x if you want. Right? As usual, you could check your answer if you want by taking the derivative of that thing at the very bottom, and you should end up with what you started with inside the integral sign. All right. Okay, one more. These ones have been fairly straightforward because you see a power of x, you choose that to be the u, and then the rest of it is the dv. Here's a little, this is a weird one. The integral of natural log of x. This is a weird one, and I don't know if this is something you've ever been wondering about. This is actually something we've never talked about. Perhaps you're wondering, isn't it just 1 over x? No. The derivative of ln is 1 over x, but this is the antiderivative of ln x, which is something we have not yet discussed. What is the integral ln of x dx? This is a weird one because it's very weird to look at that and say, I'm going to do parts, because I don't actually see two different things multiplied together. I suppose I see ln and x, but this is not multiplication. This is like a function with x on the inside. So it's weird to do it in this case, but it actually works. In this case, we are going to make these our two parts, and apparently the dx has to be the dv, and the ln x has to be the u. It wouldn't make sense to do it in any other way, but these are our two parts. Strange but true, sometimes you can just pick dv to equal dx, and it actually works and gives you something useful. So here is u is ln of x. I actually feel kind of good about that because I do know what the derivative of ln x is. And then dv is just dx, or if you prefer, you could write 1 times dx. All right. Okay, anyway, what's the du then? Anybody recall the d? If u is ln x, what's the du going to be? It should be the derivative of that. Maybe someone I haven't heard from. Surely somebody remembers the derivative. Yeah?
1 over x.
1 over x. Yeah, I think I just said it a few moments ago. This is 1 over x. You should put dx there. And then dv is 1. So v, this is also a little weird. What's the integral of 1 dx? It is x. Yeah, remember, if you're integrating just a constant, what you get is that constant times x. And since it's 1, it's just x. Yeah, great. All right, this is weird. Usually you don't choose dv equal dx, but it can work sometimes. All right, so let's do the formula. It is uv minus integral v du. We get u is ln x times v is x minus integral v is x times du is 1 over x dx. All right. Now this integral that we got here is a little weird looking, although at least it doesn't have any natural logs or anything in it. We should try to simplify. Can we simplify x times 1 over x? What do you get? Just 1. Yeah, they cancel. So that integral there, can I write the first one? I'll write as x ln x just because I find that a little easier to read. This one is just integral 1 dx, right? Simplify the integral before you try to actually do the integral. And then what is integral of 1? It's x, just like before. So this is actually my final answer, x ln x minus x plus c. And this is actually a formula that you'll see in, if you look like in the back of your book. This is a true fact. The integral of ln x is x ln x minus x. This, I'll put in a box. This is not an especially important formula. I would not expect you to have this memorized, but where it comes from is doing the integration by parts. I suppose I would expect you to be able to do the integration by parts to derive this formula. But that formula you will see in the lists of formulas. Any questions about that one? All right, I got some for you all to try. See how you like it. This one is a little similar to the one I just did, x ln x. You got to choose your parts wisely. I will put a little warning here. One of these is kind of a trick question. that one with the fraction, that's not the trick question. But the fraction you will have to deal with. Remember, integration by parts is only for multiplication. So if you see a fraction like that, you have to somehow rewrite it as a multiplication in order to use the parts. See what you think. right, can we talk about these? Because I had one more example I wanted to do before we leave, which is not all that special, but I just wanted to get to it. Maybe I'll just say the third one is the trick question. Did anybody realize sort of the trick, other than just like it gets too crazy when you try to do the integration by parts? Did anybody look at that one closely? I know not everybody got there, and that's fine. But, the last one, actually, you should not do parts. You should do the u substitution on the last one, where you choose the u to be the inside of the square root sign, and then it works out like a pretty typical u substitution. I just put that in there because the moral of the story is, if I just show you an integral, it's not always obvious which of the tricks you're supposed to use, because at least on the surface, this one looks kind of like this one. I mean, they both have x times some other stuff, right? But it just turns out sometimes when you see something like this, you want to do parts. Sometimes when you see something like this, you want to do substitution. And there isn't really a rule about which one you should try to use. Basically, you just use whatever works, and sometimes this involves trying something that doesn't work, and then you go back and try something else. This is different. This is like one of the big reasons in general why doing the integral is harder than doing the derivative. Doing the derivative, you have the product rule, and whenever you see multiplication, you do the product rule, and that's it. It's not so with the antiderivative. When you see multiplication, sometimes you do parts, sometimes you do substitution, sometimes you do some other weird tricks. Anyway, so the last one here, do the u substitution instead. Now, I like, on our tests or something, I sometimes like to give questions where it's like, here's an integral, you decide which method to use, and then do it however it works. Although, because of the way that our tests are with the big checklist, that actually is never going to happen in this class, because every question is specifically associated with one of them. So like, you will know which one is the integration by parts question. But anyway, so I'm not going to try and fool you about that, but it's something to be aware of in general. Let's talk about the first two though. So those ones are more ordinary integration by parts ones. As I was going around, people pretty much worked this one out. In this case, you should choose the u to be the ln of x, then the du is 1 over x dx. The dv must be the rest of it, which is x and dx. And then the v will be the integral of x, which is 1/2 x squared. People settled on this eventually. And then I do the formula, uv minus integral v du, which is ln x is the u, v is 1/2 x squared, minus integral v is 1/2 x squared, times du is 1 over x dx. All right? Now we shall simplify before trying to do that last part of the integral. I have the first part I'll just leave like it is. Maybe I'll write it in the other order because I like it that way. The second part, we can take 1/2 out, and then on the inside of the integral, I have x squared times 1 over x. I think of this as canceling one of the x's or dividing an x out. What remains is just one other x, right? X squared is 2 x's, and then I cancel one of them. So this is x dx. And then you do that integral. You again get 1/2 x squared from the integral of x. So my final answer is 1/2 x squared ln x minus 1/2 x squared, like that. I think pretty much everybody settled on that as I was going around. Any questions about that one? I hope it worked out. All right, let's try the other one. The other one was x over e to the x, all right? And my suggestion, which pretty much everybody obeyed, was this being a quotient, you must write it as multiplication if you want to do the parts. And to me, the easiest way, or the most convenient way to do that is to write it like this, x e to the negative x. You could write it as x times 1 over e to the x, but the 1 over e to the x is going to be a pain to deal with. E to the minus x is fairly straightforward to deal with. And now I make my u's and dv's. Anybody get this far? What'd you choose for the u? X. Yeah, generally choosing x to be u is a good idea, although not always, but yeah, so choose u equal x. dv then has to be the rest of it, e to the minus x dx. And then du is going to be just dx And v is the integral e to the minus x will, since it's a e to some power, you get the same thing again, but because of the minus, I have to make another minus out front. So the integral of e to the minus x is minus e to the minus x. All right, and now we do the parts formula. We go uv minus integral v du. It is x. V is negative e to the x, so x times negative e to the negative x minus integral v minus e to the minus x du is dx. All right. We can, I have two minus signs there which can cancel, like this minus can, this minus here can be factored out and become a plus out here. So writing it as negative x e to the negative x plus integral e to the negative x. And then what is integral e to the negative x? It is, just like we did in the previous step, integral e to the minus x is minus e to the minus x. So my final answer is negative e to the negative x minus e to the minus x. Like that. I hope you got something like that. Any questions about that one? All right, like I said, I had one more to do. We got 5 minutes, so that should work out great. One more to do. I do have just a few more examples for next time, but one more quick one for now. How about this? 7x squared e to the x. All right. You will see something interesting happens in this one, which didn't happen in the previous ones. But let's not worry about that for now. If I didn't know any better, I would choose the u to be the polynomial part and the dv to be the other part. So I'm going to say u is 7x squared. The dv will be e to the x dx. And this is the correct choice. That means the du is going to be 14x, that's the derivative, dx. And the v is the integral e to the x, which is e to the x. That's my favorite integral. All right. Do my parts formula. It is uv minus integral v du, which is u is 7x squared, v is e to the x minus integral v e to the x, du is 14x dx. All right. And now we need to do that integral. We should simplify a little bit. I can factor the 14 out, and I guess that's it. You can't pull the x out because it's not a constant, but this is 7x squared e to the x minus, okay, pull out the 14, and maybe I'll write x e to the x just because I like writing x first. All right. And now, how do we do that integral? Any ideas? This is the somewhat weird part of this. Is sort of the thing we have to do that didn't happen in the other examples. How do we handle integral x e to the x? Here's what you should not do. Don't do this. Nobody would ever do this, right? Can we just do that? The answer is no. You can't never do that. If you have two things multiplied together inside the integral, you cannot just do each one separately. I would say if you're the kind of person who's going to do that, you should have just done that at the beginning, right? I mean, if this kind of thing is allowed, then don't even do integration by parts at all. But the fact is, this kind of thing is not allowed. Like, that's why we have integration by parts. That's the whole point of integration by parts. It's like, it's an insult to the memory of the guy who came up with integration by parts. If you do one step and then this, you're like betraying your ancestors somehow. Don't do that. Another idea? Do the integration by parts again. Yeah, this is the weird step, but because I see x times e to the x, how do you handle that? You handle that by doing the integration by parts. This was actually the first example we ever did, was x times e to the x. So the moral is sometimes you got to do parts again. So I am going to leave this stuff like it is, 7x squared e to the x, whatever. Again, I choose my parts. Here I choose u equals x, dv equals e to the x. And then the du is 1 dx. The v is e to the x. And I do my parts again. So this now becomes 7x squared e to the x minus 14. That's from before. And now I go uv minus integral v du. This is the parts formula for the second time, where this time I'm using this new version of u's and v's, right? We get 7x squared e to the x minus 14 times, make sure you have parentheses here because the 14 will have to multiply by everything. uv is x e to the x minus integral v e to the x du is 1 dx. Right? And we finish finally by doing integral e to the x, which is e to the x. So my final answer is 7x squared e to the x minus 14 x e to the x minus e to the x. And I just tacked the plus c on at the very end. Right? Very sort of complicated looking answer, but it comes from parts twice. Would you believe me if I told you sometimes you have to do parts more than twice? I mean, the reason, actually it's not so hard to predict here. If you know what to look for, I can tell just by looking, sorry to scroll here, I can tell I'm gonna have to do it twice because I use x squared as the u. That means in the first step, it will turn into like just x to the 1 power. And then I'm gonna have to do it again to make the x go away entirely. So if this was a higher power of x, you might have to do it more than 2 times. All right, that'll do it. Hope you all have a good weekend. Look out for a homework assignment. I guess the homework this time will be shorter because we only met twice and we already did L'Hopital's rule on last week's homework, so it'll just be about parts.